So once again, let me ask if there are any questions, any comments, questions, anything. Okay, if not, then let's start about this. Actually, this was the content of my previous talk. I have intentionally split this talk into two, and today's talk just covers a very little bit of the new work that we have done quite recently. So yesterday I talked about the mesonic sector exotic states, which are basically the tetraquark states. So today I'm going to briefly talk about the pentaquark states. So as I told you that in the original paper of Gell-Mann, there was no restriction that mesons are made of 2 quark and diquark, and the baryons are made of 3 quarks. He himself proposed that you can always make a meson from 2 quarks and 2 diquarks, which is known as a tetraquark, and you can make a baryon from 5 quarks in which you have 4 quarks and 1 antiquark. Why we need antiquark? I'm going to tell you about this in the context of the SU3. So this story started, actually Bob Jaffe located back in the 70s about these pentaquark states, like theta states. But we haven't found any pentaquark state till the LHC started working. And this is the slide of the LHC paper in 2016, which was published in PRL. And you can see that in the lambda BD case, actually they have found a state which they call as a pentaquark state, and it is basically, it has the charm quarks as its content. It has a C quark and a C bar quark, which we always call as a closed charm states. Why closed? Because we don't have any vacant charm number rather. Because C has a charm number 1, C bar has charm number -1. Therefore, if you add the two, because these are the additive quantum numbers, then at the end of the day you have a 0 charm number. So they have found this state like in the GF psi P. GF psi is basically CC bar and proton, you know, up and down. So it means if you have a state that has quark contents like C, C bar, U, and D, you can just rearrange those quarks by using the Zweig color allowed rules. Then you can just make a state for that, which is known as a pentaquark state. So they said that this GF psi P comes from the decays of the pentaquark state. That is a resonance state. That's why you can see these resonance P's. And then there were a lot of papers written prior to the discovery of this state and after the discovery of this state. For example, this is one of the interpretation of the pentaquark state, which I told you about, just like the tetraquark states, which is a QCD bound state, in which you have 4 quarks and 1 antiquark, right? So these are the QCD bound states, like the tetraquark state. They are tightly bound states. I mean, they are bound by the gluon interaction. And then there is a molecular state. What is molecular state means? You have a baryon and you have a meson. 3 quarks rearrange themselves to make a baryon, and the quark and diquark arrange themselves to make a meson, and they interact with the van der Waals forces like in the tetraquark molecular picture. That's why this is known as a molecular picture. So I just talked about these two. I'm just skipping these kinematic effects because these two approaches we have explained in detail yesterday. So, as I told you that over-interest was in the diquark and diquark approach, so we followed exactly that approach to predict the masses of some more pentaquark state back in 2018 or 19. The idea was following. We have considered one quark-quark shell, which is known as a diquark, and I told you that if you combine 2 color triplet quarks, then you get 3 bar and 6. And 3 bar was attractive and 6 was repulsive potential. Exactly, you have a 3 bar from here. So if you combine 3 bar and 3, then from the SU3 representation, from the irreducible representation, you get 3 and 6 bar. Now if you combine that 3, which is this color 3, with this 3 bar, you have 3 bar, which is equal to 1 plus 8. So perfectly fine, you can get a color singlet from it, a color neutral meson. This is how we have formulated the pentaquark state. So the idea was this one, that these 2 diquarks are in relative angular momentum 0 state, I mean they are in the ground state. And this anti-charm quark state, which we have shown as outside this shell, it is in L is equal to 1 state compared to that. So as a whole, we can have a pentaquark state as L is equal to 0, which is a ground state, or it is L is equal to 1, which is just like the vector states we have in the tetraquark states. Once again, the effective Hamiltonian was same. This is the effective Hamiltonian that contains the masses of this diquark, and charm quark. Diquarks and charm quark is separate. This is the coupling of the quark inside the diquark. I told you that we have ignored all those coupling that lies outside this diquark shell. We have considered the coupling spin-spin interactions between the quarks inside the diquark. And this is a spin orbital term, and this is the orbital angular momentum term, and there is another tensor term which do not contribute for L is equal to 0, for the L is equal to 0 state, but that will contribute for L is equal to 1 state. For L is equal to 0, this term is 0, this is 0, and the tensor term which I'll tell you in the next slide, that will contribute. So actually this was something that we have predicted in our first paper of 2016, and you can see that 4380 is observed state, 4450 is observed state. By the way, we haven't predicted these two states. We have used these two states to predict the other states. Because I told you that in this model we have some free parameters, the free parameters like kappa, A, B. So if we know two states, at least, which are L is equal to 0, we can fix this and the mass of the diquark. This is perfectly fine. So by fixing the mass from the known state, we have predicted the new states, and we hope that in future run we will observe some of these states. But that was an old story. After that time, the LHC refined their analysis, and they said that, okay, instead of 4450, they have now resolved to two states. Because previously they have two states, 4380 and 4450. But the 4450 state is further resolved to two states, which is 4440 and 4457. So instead of two pentaquark states, now we have three pentaquark states. So what we have done is, we have slightly modified our model. Because I told you that this is not necessary that you you follow one approach. This is the latest approach that is more acceptable now in this spin-spin interaction. It is exactly, just remember this slide. We have two diquarks and a C-bar outside. Slightly change this one to this one. We have a diquark in which one is a charm quark, other is a light quark, and C-bar. There is no problem, this 3-bar will give you 3. And this light diquark is an external shell. Once again, instead of having C-bar in the external shell, now we have a diquark in the external shell of this triquark. So this is kind of a triquark-diquark picture. And this diquark is in L is equal to 1 compared to this whole shell in which we have a diquark and antiquark. It's a very simple approach. Once again, the Hamiltonian is exactly the same. Now the idea, as I told you, that for the Hamiltonian you need a state. And for the state you need the quantum numbers, right? So what are the quantum numbers that are necessary? Every undergraduate student can write the quantum numbers. You can see that, okay, they are the quantum numbers of this heavy diquark. Why this is heavy diquark? In this red color is charm, and charm is heavy. You need the quantum number of this triquark, because how the spin of a heavy diquark is combined to the spin half, because now it is spin 0. If it is added to spin half, you have a spin half. If it is spin 1, if we add spin half to it, there are possibilities that we have a spin half and 3 half. So that is why I said that then there is a triquark, and then there is a LT, which is the angular momentum of this triquark, which is always equal to 0 in our approach. And then we have the spin of a light diquark, angular momentum of a light diquark, which is equal to 1 compared to this one, and the total spin of this pentaquark state. That's all. These are the maximal quantum number that you need, or the minimal quantum number, whatever you say, in order to perform any calculation regarding this pentaquark state. So, I don't want to go into the detail of the pentaquark calculation. It's a very long paper that is around 50 pages. And here are the outcome of those papers. These are the states which we have used to fix the parameters, and we found that there is a state which is lighter than B state that has a mass of 3.8 GeV. Just to remember these are in the MeV, so you can just say that 3.8 GeV to a first significant figure, to the first decimal place. And then you can see these green masses. They lie closer to the mass that was observed at the NCP. So we hope that in the future, when statistics will improve, data will improve, perhaps we can find some more pentaquark states. And the states which we have circled, which are circled over here, they are the predictions of the older paper. So that's why we have written the old prediction and the new prediction. And you can see that some of them are very far. Why they are very far? Listen, naturally they have to be far because the approach is changed. masses are resolved, parameters become more refined, therefore these are the updated masses that we have used, that we have predicted.
What are these uncertainties?
These uncertainties arises from the different input parameters, like you can see that. We have the uncertainties from the experimental value. So we have an uncertainty in the kappa, we have the uncertainty in A, we have the uncertainty in B, and we have added them in a quadrature, and that's that. So that's why these are, these are not that refined uncertainties, but to a good approximation, if we have an uncertainty of plus minus 36 and 4300, we can say that's a good, there is no problem. So, and then we have considered the single strange, which you see that previously we have JF psi and proton. We can also have something like JF psi and lambda. And lambda has a strange content in it, I guess, if I remember correctly. And then you see that we have predicted the spectrum of all these states that are single strange, that has triple strange, like we have SSS, and that SSS state is nothing but it is omega. Then we have a JF psi and omega. So all the LHC data and the resolution is very, very good. The data sample is very good, so they can easily produce these states in next few years or so. So now this is the final summary of that talk. Previously I told you that for the interpretation of the tetraquark is through diquark and t-diquark, and the latest interpretation of pentaquark is diquark combined with a C bar to make a triquark, and that triquark is combined with a light diquark, which could be in L is equal to 0 and L is equal to 1, and using these known states, which are 3 at the LHC now, we have fine-tuned our parameters, and we have fine-tuned our parameters from some of the known baryons, which are not the exotic baryons, but the baryons, because same Hamiltonian can work for the other baryons also. I don't have a time, otherwise I can tell you that even in the lambda B, this light quark acts as a diquark because they do not change in the transition. So we have fixed those parameters, defined those parameters, and predicted the whole bunch of a spectrum of different possibilities of the closed charm tetraquark states, I mean CC bar tetraquark states. So let's wait for the LHCb, and we very much hope that in future we get some more states on the pentaquark. By the way, that is the only problem I must say with this approach, that if you want to explain 4, you predict 400. So perhaps in future we will be in a position to find the selection rules for these states, so that based upon those selection rules, we can say that only these states are possible, these are not possible. Now the selection rules are very well developed for tetraquark states and perhaps for the pentaquark state, but I am not an expert of this subject, so maybe we have to learn to gather this thing to propose some kind of a selection rules like you have in the atomic physics, that okay, there are many possible transitions, but these are not possible for the dipole, magnetic transition, etc., etc. So perhaps those kind of selection rules are also we need to develop some kind of a selection rules for these approaches also. So that's an open story as far as I know. So if you have any question, this ends the first talk, please.
So the tetraquark states which have been observed, they must have very small, very short.
Just a second.
Exactly, they are very short.
What's stopping us basically from qualifying them as particles rather than we are just saying them as states?
Okay, so what qualifies them that they are the particle and that is not a state? Okay, very good. Well, you know this problem is that when you have a resonant state, you can always write it like, suppose, let's imagine that you have a particle that is propagating, and this propagator has a momentum, right? Q squared, let's say, is a momentum. That is basically sum of the momenta of the incoming particle. If it is massive, then you have a 1 over q squared minus mw squared. So it means if it has a mass, it is a particle. So that is why I said that if it is a resonance, it's a bright Wigner, it has a mass, and then it has a decay rate. So this is exactly this is how they reconstruct the mass of the particle from this rate. And I hope Wajid will tell you a lot about these reconstruction in these tutorials also. So that qualifies for the mass because we know their decay rate, we know their lifetime, and they satisfy all the properties of the particle. They are particles, definitely, they are particles, exactly.
One more thing. Yesterday we converted the tensor product into some space. Basically that would be like SU2 is a non-invariant, so it must be having some underlying SU6 symmetry. Is there any?
There is no SU6. There is no SU6. It is just SU3. There is no SU6. Because I'm just concerned about the three colors of the quarks. And it's just SU3. Even in flavor, I have just considered the flavor symmetry. I have taken SU3 as a flavor, as a custodian Hori symmetry. U, D, S, I have their equal mass. Because breaking will give just 10% effects and nothing more than that. So this is SU3, there is no SU6. Yeah. And this spin-spin interaction is just quantum mechanical interaction. S1 dot S2 gives you iota epsilon ij k S3. SKs rather. Ij. It's exactly the same algebra. The tensor contribution is this one. You can see that Li, Si, Lj, Sj. So you can always write Li, Lj and Si, Sj as a product of something. That's why these are the tensor interactions.
So we are basically extrapolating as we can extrapolate this as an extension of the standard model.
No. We can just consider it as a new version of, I just want to use the proper word. We can just say that these are the states which we can fit the older Gell-Mann proposal, not the current Quark model. Because current Quark model says that QQ bar and QQQ are the mesons and baryons. But in the original idea, there are QQ and QQ bar as a meson also, and the 5 Quark states are also the baryons. So it has nothing to do with the standard model. We don't need the standard model for this.
Okay, so
We just need QCD.
I'll modify my question a bit. By studying all of these things, have we observed some new conservation law or some underlying symmetry?
No, we
Except
haven't.
for some of the introducing some of the new quantum numbers?
No,
we haven't.
absolutely not. Absolutely not. No, this is my absolutely not. Okay. So the idea is this one: we just have this conservation laws. If they are the strong interaction, they have to conserve parity, charge, conjugation, etc. If they are the weak interaction, they have weak interactions are the most. सबसे बागी सब violate कर रही है.
By the way, I may have interpreted in a wrong way, but you said that the UDS and UDS masses can be
Actually, flavors we can take the same mass. Equal footing we can take, and then we can study the breaking of that.
and it does not create any sort of a problem.
No.
By taking the equal masses, of course, there is not.
Exactly, yeah. And then we have to study these SU3 breaking effects. This is exactly the people did in the earlier stages when they have to detect proton, neutron, and the other particle. They said that okay, there is no problem. We can just take SU3 or symmetry, and we used to take this as a symmetry, and then we can study the symmetry breaking effects. But they are the mass effects, rather. They have nothing to do with it. Of course, their intrinsic quantum numbers are there. Strange is strange. So that remains there.
And this calculation is based on the context of the Gell-Mann model.
Exactly. This is a very precise answer. This calculation is in the context of the original thrown away piece of the Gell-Mann model. Q bar. Because we just relied on this. I have shown you this paper. Go to that slide. It's always, annoying to go back to the slides like you see. Oh, sorry. You see, I said that we adopted this as a model, and it worked very well. And this is the ordinary mesons and baryons. These are the exotic mesons because they have different quantum numbers. For example, QQ bar in L is equal to 0 has a negative parity, but Q bar in L is equal to 0 has a positive parity. That because of the quantum number, they are exotic states.
By the way, we have written etc. That means
Exactly.
it's very trivial to accept.
Exactly.
But if it's very trivial, then is there any study you already done?
Yeah, no, I have seen a paper almost 2 months ago. People have written about this hexa quarks. Yes. 6 quarks. Hexa is 6. Hexa quark states. 6 quark. Q bar. But life works on a reduction principle. We don't want to make life to be very complicated. Perhaps if these states, we can fit these states in the ordinary meson and baryon, that was very fine. There is no problem. There is no debate. But we can't. That is why we have these as a new state, because the quantum numbers are different from the ordinary quantum numbers of the mesons in the case of tetraquark state. That's why they are exotic states. And we have to extend these quark complex. So any other question? Otherwise I can open my... Yes, please.
So what are the common decay channels of tetraquarks?
There are many. There are many channels that are possible, It's a very good question. There's not one. There are many channels that are possible. But because, the C quark can decay to anything. There are weak decays, there are strong decays. There are different possibilities. There are different possibilities. And in that paper, I think I have written somewhere its reference. If not, I can give it to you.
And of course, the follow-up would be the biggest, largest branching fraction to the Higgs channel.
Exactly.
And that is electronically or
If their mass is above the threshold, I'm going to talk about this threshold effect. If the mass lies above this threshold, then it will strongly decay. If not, then it is weakly decay. And weak decays have their advantage because you can just look at them at the vortex. You know better than me. So this is the older paper of 2016, and I'm not sure if yeah, here is the new paper. Yeah, exactly. This is 2019. It's a very long paper. Tasneem is an expert. He's way better than me. He's working on this one, except his times are done.
So if there is any signal instead of CC bar, we have PB bar or U bar?
In the tetra box, yes. In the tetra. I'm going to quickly talk in 15 minutes about that stuff. And there is a story behind this calculation also. Okay, so as you see, yesterday someone asked me exactly the question, which is a simpler version of the question of that do we have the B quark in the tetra quark or penta quark states? My answer is yes. We can have a single B and a double bottom quark even. And this is we have already done. And these are the states that we have written downstairs. You can see why B downstairs. And this B signifies the presence of a B quark. By the way, the story started with a very simple calculation. My colleague Ishtiaq, who is working at the National Center for Physics, and myself, we visited Professor Ahmed Ali in Daisy, and we were reproducing that paper of X387. And Professor Ahmed Ali asked us that, okay, perhaps there's a good idea to see if we can extend this calculation to BB bar also. And we did. It is always good to have a smart person in the group. An expert is Ahmed Ali and smart is our colleague Christian Hampour. We have done a simple calculation. We don't know what will come out of that calculation except that spectrum which we have. But the Christian Hampour was very smart. He was a PhD student at that time. He knows how to do the data analysis, and this was a theoretical physicist, by the way. And he used this route, and he said that, okay, then in the Bell data, they have missed this peak. It's a tetra quark state, that's why I don't want to go into the debate of that once again. He said that in the Bell data, they have considered, for example, this state, but they have missed some peak. So he said that if we include this peak, then the chi-square fit becomes better. This peak is visible, perhaps their resolution was not that good in their fit. So he predicted that. He said that, okay, together with us, he was the main, and Ahmed Ali was the main driving force for that. And he said that this state might be the tetra quark state that we have predicted as 10, 8, 9, 0, something like that, if I remember it correctly. 10.890. It is not an upsilon state. What is upsilon state? Upsilon state is a B bar state. So this state has a B bar and the 2 light quarks, right? So, and this state we have advocated at that time and we said that, okay, this state should be there, and Bell has to rescan their data. And then in the further calculation, because I just quickly want you to finish this topic, in the further explanation we have done this calculation and we said that, okay, let's do this Bell scan and calculate this di-pion mass invariant spectrum, just I said that strong decay spectrum, and see if we can improve the data. And we have calculated the decay by using F0, the scalar state. You remember I told you that these scalar states are debatable. They are the tetra quark state, right? Do you remember this one? We have considered in the yesterday's talk. I told you that these scalars have inverted triangle, and they are the tetra quark state. So by considering the tetra quark state, we have calculated the decays of YB to upsilon 1 as pi pi. This is the natural decay of the upsilons with higher upsilon states goes to the lower upsilon states and the 2 pions. So instead of the upsilon, we said that this is a natural decay of a YB state to upsilon BB bar and 2 like UU bar, and the further U and U bar or DD bar will pop up from the vacuum, and we have this state as a upsilon pi plus pi minus. And we have found that this pi plus pi minus can also come from F0, because F0 is a 4 quark state, so there is no problem. Pi n has a quark anti-quark, and the other pi n has a quark anti-quark, and F0 has 2 quark and 2 anti-quarks. So by considering all the decays which are written in this paper in Physics Letter in 2010, that was a follow-up paper, we have just rescanned the data and we have proposed that, okay, YB state should be there. And Professor Ahmed Ali said that we encourage the Bell to rescan their data, and they did, by the way. And you see, they haven't found this, they said that okay, they haven't found this YB10890, but they found ZB10610, which is fair enough, which is very good. At least we have a concrete evidence of another state in the B sector, which is Z, that comes from this decay, And they found this kind of a state, and this was a paper which later Ahmed Ali and Professor Ahmed Ali and his collaborator Wilman and Christian Handu, they have written, and by the way, they have corrected the mistake in our earlier paper also. That's why this shows, this is not the second paper, this is erratum in that paper. There was a mistake in that paper, and they have corrected in this paper also. So the whole idea to tell you is that in the 2010, we proposed a state as YB. We said that, okay, that is just like the X3870, but in the BB bar sector. We encourage the bell to rescan their data, and for example, and then in the later studies, Ahmed Ali and his group, they have extended this calculation, and they have considered further, they have refined this calculation in a very fine way. They have a series of papers on this topic, and all those papers are published in Physics Rev Letter or something like that. And then they have advocated different states, and some of them were found experimentally at the different experiments. So this story still goes on, It's still an open question, it's still an open field. There are many states that are there. There are many scans that are needed at the experimental sites, and this story should go on. So this is the only thing which I want to talk about, the PV state. Now coming to the aftabs. This is something which is technical, which is previously that was a simple Hamiltonian calculation. Now the second part of the talk is the decays of because at the end of the day, in the experiments, we have to look at the decays, We have to consider all possible decays, theoretical possible decays, and from that decays, we calculate the total decay rate, and from the total decay rate, we can calculate the branching fraction of an individual decay. Why I say total decay rate? In experimentally, they just measure the lifetime. And lifetime, inverse of the lifetime by taking H bar upstairs is just the total decay rate. And now we have to calculate the branching fraction. Branching fraction tells you the probability of a particular decay in an IV sense. It is a probability. For example, if some decay has a 1% branching fraction, it means its probability is 1 in 100, right? So I'm going to talk about these decays now. As I said that, now there are the states that are located both at the lattice as well as at the experiments is double jump. You see CC. Previously we don't have CC states, we have CC bar states, remember? I tell you X3872 has 2 jump quark, but they are C and C bar closed jump. These are open jump states. So they have jumpness equal to +2 if you define jump C. So jumpness of a jump quark will be +1, then this is C is equal to 2. And their radii is bigger, slightly bigger. They are the bigger state. That's why people said that they are the molecular states. And if they are the molecular state, they have to decay strongly, for example. But the problem is the following. Problem is that from the lattice calculation, we know that the mass of these states lie just below the threshold of D0 bar. D0 has a quark content of a C, and let's say D0 you can say, D star, whatever you can say. They have CD bar, they have jam and other is CD bar. If their masses is slightly lower than that, it means they cannot decay strongly, then they decay weakly. What are the weak decays? Weak decays which do not conserve parity, charge conjugation, etc., etc. So if these states are there and their masses lie below the threshold of the respective D mesons, 2Ds, then they decay weakly. So that is the whole idea that we have considered. We have considered from the lattice, these are the, now we know this baryon which has a BC, 2 heavy quarks. We have the tetra quark which has BC, and we have single bottom tetra quark, double bottom tetra quarks, single jump tetra quarks, double jump tetra quarks. So all these states are there. The problem is the following, that their masses lies below the threshold. Therefore, one has to study the weak decays. And that's why I've written that. You see that change in mass is -100. It means you have to put in 100 MeV mass to let them decay strongly. It means they lies 100 MeV below that. And the other is 30 MeV below that. These are from the lattice calculation. 2 lattice papers are there. So what we have done is we have considered these decays. Yes? From lattice QCD, exactly. From the lattice QCD. हाँ, lattice calculation. हाँ, मैंने कहा था अगर कहीं पे एक्सपेरिमेंटल प्रेडिक्शन हमारे पास हैं, तो अगर तो नहीं है तो हम लैटिस QCD पे रिलाई करते हैं, ऐसा नहीं था कि लैटिस में नहीं जाते। वी कैलकुलेट द फॉर्म फैक्टर फ्रॉम लैटिस। मेरा होल आइडिया ये था कि उन स्टेट्स के लिए हम लैटिस पे लेंगे तो एक्सपेरिमेंटल उसमें, हाँ, वो नॉन इन एक्सपेरिमेंटली स्टेट उनसे यूज करके। यहाँ मसला कुछ स्टेट्स बिलो द थ्रेशोल्ड लैटिस कैलकुलेशन की जाती है। जब रिफाइन नहीं होता तो लैटिस हमें हमेशा एक विंडो दे देती है जस्ट लुक एट दोस स्टेट्स के वो कहाँ लगते हैं। लेकिन अल्टीमेट जो चीज़ है वो एक्सपेरिमेंट से आएगी। अगर हमें कभी एक्सपेरिमेंट से कोई चीज़ मिल जाएगी फिर हम लैटिस की कैलकुलेशन को नहीं देखेंगे, फिर हम एक्सपेरिमेंट्स की एक्सपेरिमेंटल वेरिफिकेशंस को ही देखेंगे। तो द वीक डिकेज which we have considered is the, you see, what's the difference between these two states you can see? Anyone. One B goes to John, right? You know B has a charge to be -1/3 and U has a charge, John has a charge to be +2/3. It means you have, in order to have a charge conservation, you have to have a boson that carries minus charge, and you know that in the standard model that is W minus. And W minus will go to any electron like electron, muon, tau 1 and the respective neutrino. So these are the standard model decay. And even you can see that B to C, W can also goes to UD bar, right? Or U bar D if it is W minus. It means you can also produce pions, rho meson, and many other particles. So this is why we have considered this. BB and then we have BC. Again B goes to C, and in one case we have double charm tetraquark state in the final state. In the other case we have a bottom charm tetraquark in the final state. So these are the doubly heavy tetraquark states, not singly heavy tetraquark states. By the way, there are the possibilities that this BB goes to baryon and a proton. These decays are also possible, but unfortunately we don't know how to calculate them at the moment. We are thinking about it. We are just trying to understand some older literature on this decay, but we don't know at the moment how to calculate this one, because this is our next project. And honestly, I don't know how to. At least I don't know how to calculate it. And now the idea is, I left the question, how to calculate these decays even. Anyone who has worked on the bound states, he or she knows that once you have the bound states, you cannot do the exact calculation. I told you that QCD has a distinct behavior at the two energy scales. At high energy scale it is perturbative, at low energy scale it is non-perturbative. And I told you that in the non-perturbative you have to use some model. And if you calculate the decay, this decay involves the matrix element of these two decays, and these two decays involve the form, and these matrix elements involve the form factors. Form factors are kind of a structure function, right? And these are the model dependent calculations. They are the source of uncertainties. But how to calculate these form factors, that is a problematic way, because then we have to develop some model, and people have developed QCD some rules, Lightroom some rules. There are there are a whole bunch of models that they have developed. And I'm going to tell you which model we have used to calculate. And these are, by the way, I always dislike to write the calculation, but someone asked me yesterday, what is the effective Hamiltonian? Yes, someone asked me during the lunch break that what is effective Hamiltonian? Here I have written the effective Hamiltonian. Effective Hamiltonian is what? You choose an energy scale, right? For example, you say that a particle, electron positron, they are coming, they goes to W, and W has a very high mass compared to the energy of these two particles. It means you can ignore the Q squared compared to this MW squared, right? This means this theory is valid in the approximation that your energy scale is much smaller than the W mass scale. That is why this is the effective scale for this theory. Exactly the same effective scale we have used. We have considered the W to be very heavy and these two particles come very close to each other. Then we have just used a standard model, and you know standard model is an effective theory. So these are the operators for the electron. That V goes to C, these are V minus K, V in vector, axial vector operators, and this is the electronic current. What we have done is we have used the heavy quark effective theory. Heavy quark effective theory is what? Heavy quark effective theory says that light quark has nothing to do with the dynamics, it's the heavy quark that has to do, and heavy quark is almost, its whole energy, its whole momentum lies in its velocity. You can always write it as, momentum is not equal to mc or mv always. Its momentum is mq into v plus some small momentum k, and that is a residual momentum that goes to these remaining quarks. This is an active quark, and these are the spectator quarks. So this small momentum, residual momentum of shellness goes to the to the other quarks which are not taking part in the decay. So these are two representative diagrams for BB and BC decays. They are
Is it because of the mass it makes it as an effective quark?
exactly it's an effective theory because W is much heavier compared to the energy scale, V and C's. So that's why you can see that Q square is, you can ignore it, you can always write this as a Fermi coupling.
Because I was thinking that if B decays to the C, then it can also couple with the C. Because B and C are...
Exactly. You are very right, but you know we said that they are bound. So they cannot annihilate each other in the QCD. Otherwise the state won't exist. So there is no annihilation inside. This is just rearrangement of the quarks. And by the way, in the heavy quark effective theory, you can always write the projection operators. People have done these calculations for quark anti-quark state, for B decays. And this is very mature in the B decays. This approach is very much refined in the B decays. So what we have done is we have adopted that approach in the tetra quark, which has never been done for the tetra quark, by the way. We have considered initial and final tetra quark state. You can see that we have written velocities instead of the momentas. And you have these as H1, H2, H3, H4 as the form factors. Why these are H1, H2? You can give them any name you like. These are the structure that comes from different Lorentz structures. These are all possible Lorentz invariant structures that are possible in these decays. So why heavy quark effective theory is used? Heavy quark effective theories are always used to reduce the number of parameters, number of form factors. So the heavy quark effective theory is used to reduce the form factors. And what we have done is you can see that H plus, HV, HA1, HEP, they are related to single form factor. And you know if you have a one unknown, there is no problem at all. You know something decay rate, everything is known except this unknown, and you can predict or calculate the value of this unknown from that. What we have done is, because these are we have related them to the form factor of D to D star. Because B is a quark anti-quark meson, D is a quark anti-quark meson. So we have related the form factor of the tetra quark with the form factor of the Bay meson with this normalization structure. Perhaps you ask that what are the physical motivations for that? The physical motivation is we do not expect that the form factor for the tetra quark to be as high as that of the B because the tetra quarks have much larger masses. That's why we have considered this ratio of the masses. We don't have any theoretical background for it. We just have a motivation that we can always use these kind of intuitive factors for that. So by using these factors, we have calculated the decay rate. And you can see that the decay rate is 1.2% and 0.53%. It's a very, very small decay rate. It's too small, 1.2% just. That is why I said that these are the stress decays. And then we have calculated the hadronic decays also. Instead of the L, mu L, you have the hadron in the final state, like pi on, rho, d, etc., etc. The calculation exactly remains the same. And these are the rates which we have calculated. They are all of the order of 10 to the power minus 3. They are very, very small numbers. They are few percent. I mean, they are, let's say you can say that 0.5 to 2% or nothing more than that. So these are the estimated branching ratios of these decays. These are not in the limelight at the moment. What I mean by this thing is, people are not looking at this for the time being because we are still waiting for the LHCP to take some more states and see if the states lies below the threshold or the above threshold. But the important thing is, now we have the well-controlled theoretical estimate for these decays. And we can use these estimates if these states decay via weak interactions. We know the theoretical value of their branching ratios, at least estimate of the branching ratios. So that was the whole idea to form this calculation, and then we have extended the same calculation for the other states. So let me summarize this at this point. I have to read it and then I will explain it because this is slightly different from the previous slide. This is technical one. The heavy tetra quark states are stable against strong interaction. What do we mean by the stable against strong interaction? They cannot decay to dd bar because their mass lies below the threshold. So that's why I say that they are stable against strong interaction, but they are not stable against weak interaction, and they have to decay weakly. And we know that in the initial state and final state, we have the tetra quark state, and we don't know how to calculate the matrix elements. Therefore, we have to use some kind of effective theory. So we use a heavy quark effective theory. The idea of this heavy quark effective theory is that we can reduce the number of form factors, and we can relate those form factors of the tetra-quark state to that of the B to D decays or other decays which are possible. So in this way, from the known form factors of the B decays, we can estimate the form factors of the tetra-quark states. And once we know the form factors, that is the only unknown quantity in the calculation, we can predict we can estimate the branching ratios of the different B decay modes. And the final is, these will be observed at CMS, Atlas, LHC, eventually, if not over here, then eventually at Terra Z factory, which are basically these machines that can look for these kind of states very, very precisely. Of course, after the additional support from the lattice, because lattice has its own artifacts, once this computational facilities will improve, lattice calculation will improve, then these estimates from the lattice will also improve. So once we have all these things, we get a better control on the masses of these tetra-quark states, and if they lie below the threshold, then we have to look for these weak decays. And this whole thing you can find in the, perhaps that paper you find too technical, but if you are interested, I recommend you to read the introduction of this paper. Because in the introduction, there is a whole story of these things. The introduction is written is written not for the very expert but people. That was written by in a very nice way by Professor Ahmed. So everyone who is interested, he or she can look at this paper. And if you have any question, you can always send me an email, or you can come over to Haidar University from next week onwards, not this week. So thank you very much.
Thank you very for beautiful lecture. Any question for the speaker?
आप पूछने वैसे चलें।
Some of these states might be vector states, right? Some of these exotic states might be the vector states.
Vector means 1 minus, yes. Yes.
So how are we going to study their polarization? Would that still be?
There's no problem at all. There's no problem. You can just, there are two possibilities. You can study the polarized decay rates. And that will tell you the probability of a particular polarization state. And people are doing it a lot for the P2 vector, B2 K star, B2 K1, P5, FL symmetries, S5, etc. Exactly. That way. Exactly you can do it. Exactly. This you can see this JP is 0 plus to 1 plus. This is a scalar, this is a. Okay, so. Okay, why they decay weakly? I said that the mass lies below the respective meson states like D and D0. D bar, you can say D star, etc. So if the masses lies below that state, they cannot go through these, they cannot decay strongly, then they have to decay weakly. Or electromagnetically, but these are the weak decays that are possible.
You can multi-quark.
Yes, exactly. Thank you. There are two papers of Professor Ahmadari on this topic. One is with Cyril Launch on the multi-quark state. That's a book published by Cambridge University with Luciano Manani and Pelusa. And the other is the archive big lecture that discussed this whole bunch of approaches. I forgot to mention that the pictures which I took in my slide, these fancy tetra-quark, that were drawn by Christian Handel for his PhD thesis. So I asked him and he sent me at that time, and I am still using them.
Sir, my question is the effect of large number of color flavors on QCD phase diagram.
Question about large number of colors on the QCD
phase diagram.
Flavor diagram. So question is what?
Yes. This question. The effect of large number of color on QCD phase diagram.
Okay, right. So okay, very good. So you can always work on the large NC limit. There is no problem at all. You know that once you make the color rearrangement, you can write some color singlet set and 1 over NC times something. And we used to work on NC goes to infinity, infinite color. There is no problem. There is absolutely no problem at all. This take care of every single thing.
Thanks.
It's a very, very good question. That's by the way, technical question, and you can create these masses and spectrum. So in Professor Ahmadari's book, there is a separate thing of discussion on this QCD algebra. So I recommend you to read this appendix of that paper. That is written very nicely, by the way. And one paper by Isadori and Pelusa, they have calculated this NC spectrum of different color states.
Is there any other question?
What are the big questions?
तो आप क्या assume कर रहे हैं या क्या एक्सपेक्ट कर रहे हैं कि ये कुछ अनआंसर्ड क्वेश्चन के आंसर कर सकते हैं, जैसे कि फॉर एग्जाम्पल पहले ने इसमें किया जैसे LHC के एक्सपेरिमेंट है।
पहले तो बात है, ये बजाते खुद एक क्वेश्चन है। इसलिए क्वेश्चन है कि ये वो चीज़ थी जो पुराने तरीके से एक्सप्लेन नहीं हो पा रही थी। ये खुद एक सवाल से जन्म लिया इन्होंने कि ये वो स्टेट्स हैं जो ऑर्डिनरी क्वार्क मॉडल में फिट इन नहीं होती। तो ये QCD स्टेट्स हैं जो क्वार्क मॉडल एक्सटेंड किया गया है, क्वार्क मॉडल को आप ये समझ लें मॉडल दौर में थोड़ा सा इन स्टेट्स के लिए। ये तो है एक ये क्वेश्चन से शुरू होने वाली स्टेट है जो ऑर्डिनरी मेजन डिके करके जिन चीज़ों में डिके करते हैं और जिन मॉडल्स में डिके करते हैं। फॉर एग्जांपल यू नो पीपल आर स्टडीइंग दिस बी डिकेस यूजिंग Z prime supersymmetry etc etc. You can also study those effects in these tetrapod states. So if my answer to this question is they give you the same, they are way more complicated to calculate. Perhaps they don't add any new insight in beyond standard model decay. Because the decays are the same. Because B to C decay is the same whether it is in tetraquark, whether it is in B meson, whether it is in upsilon, anything. So they don't add any new knowledge in this fundamental symmetries of this work. Standard model जी।
सर क्या ये एक्सोटिक जो हेड्रोन्स होते हैं ये कन्वेंशनल मतलब हेड्रोन्स को समझने के लिए हमारे लिए हेल्पफुल हो सकती है या
आप सारे ऑर्डिनरी हेड्रॉन्स को भी ना कन्वेंशनल एक्सोटिक मान के चलें तो क्वांटम नंबर्स की हुई है, लेकिन प्रॉब्लम सारा ये है कि ये वो हेड्रॉन्स हैं जिनके क्वांटम नंबर मैंने पहले कहा मुख्तलिफ हैं जो क्वार्क मॉडल से मेज़न आते हैं। मसलन मैंने कल भी बताया था कि क्वार्क का जो पैरिटी है वो +1 है, एंटी क्वार्क की -1 है और इनको मल्टीप्लाई करते हैं L0 में तो +1 × -1 और -1 टू द पावर L होता है L0 हो जाए तो इनकी नेगेटिव पैरिटी होती है। लेकिन अगर आप इनको देखें एक क्वार्क की भी नेगेटिव पॉजिटिव है, दूसरे की पॉजिटिव +1 होगी डाई क्वार्क की, एंटी डाई क्वार्क की भी -1 उसकी भी +1 होगी, तो टोटल पैरिटी कितनी +1 होगी। तो ये है तो मेज़न, लेकिन इसकी ग्राउंड स्टेट में पैरिटी +1 है जो कि -1 होनी चाहिए। दैट्स व्हाई वी कॉल दिस एज एन एक्सोटिक स्टेट। फ्री क्वार्क एग्जिस्ट नहीं करता बिकॉज ऑफ द एसिम्प्टोटिक फ्रीडम है एंड कन्फाइनमेंट। आप उसे इलादा करते हैं ना, वो कहीं और से ग्लू से ना फ्लक्स ट्यूब से पकड़ के दोबारा वो दोबारा उसको बाउंड स्टेट बना देता है, अकेला नहीं रहता। जी जी। इसलिए कि मैं पता है ना कि QCD के लिए मैंने आपको बताया था कि QCD 2 डिफरेंट स्केल होते हैं। यू नीड अ वेरी हाई एनर्जी टू फीड अ क्वार्क, ठीक है। लेकिन दो बॉन्डिंग जो मॉलिक्यूल्स के दरमियान में आप आराम से ब्रेक कर सकते हैं। जी जी, मैंने कहा था कि अगर वो QCD से बाउंड हैं तो ग्लूऑन एक्सचेंज है जो कि स्ट्रॉन्ग इंटरेक्शन है। लेकिन अगर वो मेज़न बना के बाउंड होते हैं, मेज़न बना है QCD से, एक मेज़न भी QCD से बना है, दूसरा QCD, लेकिन जब दोनों मेज़न बन के इंटरेक्ट किया तो पाइऑन या कुछ भी एक्सचेंज हुआ है वंडरवाल फोर्सेज आप उनके देना। जब वैसे लूजली बाउंड मॉलिक्यूल उसका साइज बड़ा है, और मैंने कल जिक्र किया था कि साइज का PT से भी पता चल जाता है, जो ट्रांसफर मोमेंटम डिस्ट्रीब्यूशन होती है वहाँ से तो हम देख सकते हैं कि वो कितना कॉम्पैक्ट है, ठीक है। तो जो ग्लूऑन से बाउंड है वो QCD है। हर मेज़न जो बना है वो QCD से बना है, लेकिन जब मेज़न बन गया दूसरे मेज़न के दरमियान आया तो फिर उन्होंने आपस में वंडरवाल इंटरेक्शन की।
हम we are running short out of time, so please if you have any question,
मुझसे पूछना
Jamil at the line. So Jamil, thank you very much for your lecture and for showing time for this school. And I request to Dr. Quark Sahib, please come on the stage to present souvenirs to Jamil.
अच्छा, इशफाक भाई मेरे उस्ताद हैं, मैं हर दफ़ा बताता हूँ, ये मानते नहीं।
टीचर हूँ मैं इसका। So we are really thankful.
अच्छा, मैं कल शायद ना सकूँ, लेकिन मैं नेक्स्ट वीक पूरा रेगुलर आऊँगा, तो आपका कोई भी सवाल हो तो हम